Homework 3, Part D. For Part 1, we're going to derive the Laplace transform of a time-shifted function with a dead time of theta. So to start off, what other problems of this homework have looked like is we have a function and we simulate the response over time, and we have some oscillations with it eventually reaching its set point. So if we're looking at the concept of dead time, let's say we have a function that looks like this, and we're going to call it f of t. So a dead time or a time delay would typically be implemented because if you have a controller, if you have a PI controller, a proportional only controller, it's not going to work immediately. It's going to take a certain amount of time for it to start working. So that's what we call our time delay or a dead time. And so we're going to call that theta. And so there's a certain amount of time here that would take for the controller to begin working. So it'll be a delay. So we would shift our f of t function. We would shift it, that theta distance. So if we redraw it, it would look the same, except it would be shifted. And it would still eventually reach the set point. These two lines would eventually meet. But again, there's this time here. There's this period where the function is at 0 for a time of theta. And so we can write this out as f of t would equal f of t minus theta, because it's being shifted. And then we also have to multiply it by a unit step function, because if we simply just shifted it that amount, it would go up and down too, but we want it to still start at 0 at this time. So it would also be u of t minus theta. And so now we have to derive the Laplace transform of this function here. So take the Laplace transform of this. I'll write that out down here. So if we take the Laplace transform of this, it would look like the integral from 0 to infinity of f of t minus theta times u of t minus theta, and then times e to the negative st dt. And to simplify this a little bit, we can define t minus theta as tau. So therefore, t would equal tau plus theta. And so let's rewrite this. It would equal, just go down there, but it would equal the integral of f of tau times u of tau, and then e to the negative s, and then we would replace t with this tau plus theta. And we also have to shift these bounds here, because we are writing this in terms of tau. So if we plug in 0 for our t value over here, if we plug in 0 for that, we get tau equals negative theta. So that would be our lower bound. And then if we plug infinity in for t, we would still get infinity. But if we look at our theta value here, our dead time, our time delay, it's never going to be a negative value. It's always going to be 0 or greater than 0. So instead of writing negative theta right there, we can just write 0. So the bounds technically will just stay the same. And so we can rewrite this again. It will equal e to the negative s, and then theta, and then times our Laplace transform right here. So this is our Laplace transform of our time-shifted function with the dead time of theta, right? And now we can move on to part 2. So we've done part 1. So part 2, we have to determine the Ziegler-Nichols ultimate controller gain and period for a first order system with a dead time of 0.1 seconds. So that is our theta, a time constant of 1 second, that's our tau, and a gain of 1, so that is our k value, and yeah, all right, and then our ultimate controller gain is kc. So now we will move to Colab to simulate this. All right, so I have imported our tools here, and we can start by just defining some of our variables. I'm just looking at my iPad here. So we have our theta to be 0.1 seconds. So theta equals 0.1 seconds. And then we have tau as 1 second. And our gain k is equal to 1. Oops, not that. And then we're just going to make our kc 10 right now. No, okay. And then we have our gc and our gp, our transfer functions. And our gc is equal to kc times, and then we'll have 1 plus, and it'll be 1 over tau I, which we'll have to define, times s. Make sure we have enough parentheses there. Yeah. And then we'll have a tau I as well, which I will just define as 1 for right now. And then we also have our GP, which is the transfer function of our entire process, which is k times exp, so e to the power of negative s times theta for the numerator, and then in the denominator we have tau times s and then plus 1. All right. And then we have to define our G closed for our closed loop function, which is going to be all of our transfer functions in the forward direction and then over all of them in the open loop. So it's going to be GC times, right? GC times GP divided by 1 plus GC times GP. Right, and then we should be able to just go ahead and simulate this. So we will know our outputs will be time or T and H. Usually we have done this with our output variable being height. It doesn't always have to be that, but for now we're just going to call it H. So we want to simulate our G closed. We want our time and T1. and then we'll make n 1000, and we'll make our dt equal to 0.1. So now we can go ahead and plot this out. So fig equals make underscore subplots, and then fig dot add scatter, and then our x will be t, our y will be h, and our mode will be lines as it usually is. Then we can hopefully just press shift enter. Okay, so that does not look right. Okay, I think I actually just wanted to set this to 0.1. Okay, that looks much better. So this is what our graph is looking like without the Ziegler-Nichols method. So as you can see, there's a lot of oscillations here. So let's go ahead and look at our Ziegler-Nichols method. So we are doing a proportional integral controller. And what this is saying is we want our Kp to be 0.4 times our ultimate controller gain. And we also want 0.83 times our TU value, so our tau. So we can go ahead and type this into here and change these variables. So our tau I is going to be 0.83 times TU. So we'll change that. So it'll be 0.83 times TU. And then we have to define a TU as well. So we will say TU equals 1 for now. And then we want our Kp to be 0.45 times Ku. So that is our Kc value. So we will do 0.45 times KCU, and we will define KCU as well. We'll just say that 13.83 because that is our ultimate controller gain. And I believe that is all we need, right? Okay. So our TU actually is 0.35. All right. And this is supposed to be 0.01. Okay, that looks a lot better. So as we can see here, it has, if we zoom in down here, we can see our time delay. Yeah, so we set our time delay to 0.1 seconds. So that looks good. And how do I get out of here? Oh no. Okay, there we go. So we can see it reaches our set point eventually relatively fast, and it has this overshot here and then it comes down. So that is our Ziegler-Nichols method, and that is that's part 2 of D here. And now we can repeat that with using the Smith-Corripio ITAE open loop tuning method. So those have some different parameters, which we can see here. So we are using a PI controller, and the type of input we have is a set point. So we're going to use these A and B values right here to simulate this. So I'm going to start a new thing down here, and I'm just going to quickly write these constants on my iPad so I don't have to keep going back and forth. Right, so I have this written on my iPad here, And we can go ahead and code this. So our PA is equal to 0.586 right here, which we can see right here, 0.586. And then we will use our PB will be this negative 0.916. So we can write that. So PB equals negative 0.916. And then our IA value, so this next row here will be 1.03. So 1.03, and then our IB value will equal negative 0.165. And we also have to take into account this design relation, so this Y here. And so we can write that as well. So our Y will equal PA times, and then we can see what it says, PA times theta over tau. So theta over tau, and then to the power of B. So to the power of PB. And then our KC will equal Y over K, I believe. Yes, our KC will equal Y over K, just rearranging that bit right there. And then we also need to calculate tau I from this expression. So it'll be tau I equals tau in our numerator, or we don't need that. And then divided by, and we'll have IA plus IB, and the IB will be multiplied by theta times tau. Sorry, theta divided by tau. Okay, and then should just be able to copy and paste this because it is the same process, so we'll have the same transfer functions. All right, and so we can see that with the Smith-Corripio method, this tuning method, we still have this dead time down here, but we can see here we barely have any of the overshot that we had with the Ziegler-Nichols method. We had this overshot that went up to almost 1.6, and here it's very, very minimal. Let's see if I can zoom in there. Yeah, it's very minimal, not even going to 1.01. So this could be a better method depending on the process or what the function is. But yeah, I believe that is all the parts of our homework here. So I will see you in the next